Hello, everyone. Thank you so much for joining us today. We have got a great webinar set up for you all, and we are so excited to share the next hour or so with you. I'm going to give everybody just a minute to get logged on and join us. So we are live on LinkedIn and on YouTube. So feel free to drop in the comments where you're joining us from. So I am joining you from South Georgia. My name's Kinsley, and I'm one of the CSMs with High Counselor. And so I am in the South Georgia area. And I am with Sagar. He is here with us today. Where are you joining us from?
Yeah, I'm joining in from Seattle, so I'm excited for this talk and hope it can be helpful to people.
Great. Let's see. It does look like we've got some people commenting, so thank you for sharing where you're located, where you're joining in from. I think it's always interesting to see all the different time zones and locations that are represented. So thank you again for sharing. So like I said, we've got about the next hour together, and we've got some really great information to share with you. I'm going to give you just a really quick rundown of High Counselor. So I do want to share with you that we are a career accelerator, and we help job seekers land their dream job through about a 4-week training period. We cover important topics and concepts that are typically asked during those interviews, and so sessions on behavioral, HR, technical interviewing. We help candidates optimize their resume and LinkedIn profile. We also host sessions on networking, salary negotiation. We've got some one-on-one sessions and mock interview prep to provide candidates, and then also some group settings. And so a lot of good resources that are available for you through the High Counselor program. We've got automated email networking, automatic job applications, really just helping to reduce some of the burden of the job search process. We also offer real-world projects, so definitely want to encourage you to check those out on our LinkedIn Live. So we host a variety of data science and software development projects, so check that out as well. And then I'm also going to be dropping some links in the comment box at the end of today's webinar for you. That will include the sign up for those live projects, along with the opportunity to learn more about High Counselor by attending one of our info sessions. I know this was a super quick overview of what High Counselor has to offer, but we do host info sessions every week on Tuesdays and Thursdays at 7 p.m. Eastern Time, which means we have a session tonight. So if you are looking to get more information about High Counselor, feel free to sign up through the link that I will be sharing at the end of the session. And then just so you know, our next cohort start date is October 30th. So you've got a little bit of time to learn more about High Counselor and see if it is a good fit for you and a resource that you can use. So with that, I'll get to the real reason that we're here. And we're focusing, as you all know, on breaking into the world of large language models. And so our guest is a senior NLP engineer at DeepScribe, a robust AI-based documentation solution that totally transforms the doctor-patient experience, giving time back to doctors, which is always great. In this role, he works on cutting-edge NLP solutions to create detailed visit summaries for physicians. Previously at Snap, he worked as a machine learning engineer where he built large-scale distributed recommendation models for ranking lenses, making use of NLP and CV features. Prior to that, he worked at Microsoft as an applied scientist, an AI researcher at Max Planck Institute, and has completed his bachelor's in technology from IIT Delhi in CSE. At Microsoft and MIT, he worked at the intersection of deep learning, NLP graphs, and recommendation systems. So you guys are in for an absolute treat. What a bio. So with that, I'm going to go ahead and hand it over to you. I know you've got a lot of really good info that you are ready to share with our viewers. So thank you again for being here, and we are so excited to learn from you.
Yeah, Thank you, and I'm super excited for this talk as well. I really am hoping that I can help people get into the world of large language models, break it down, and anybody who's interested, they can probably start thinking about the next steps that they want to take in their career. So right away, getting into it, it's going to be a mix of technical as well as career-related discussions. But the primary topics that we'll be touching on will be a very basic intro into what large language models are exactly. Then a little bit technical session about how they work, a bit of the history and what basically ChatGPT looks like. Then some quick discussions about real-world applications and challenges with LLMs. And then we'll have a quick question answer session, and after which we'll go into the part two, where we'll be talking more about the career aspect of this field and how somebody who is willing and interested in this can break into the field. Yeah, feel free to drop your questions. We'll take those questions in the Q&A rounds as we get to them. So starting with something like what is a language model? It's basically a tool that is supposed to generate human-like language, and the caveat is that it's usually trained on large amounts of data. A quick example is like you have a certain set of words, a cat is chasing the dash, and the idea is you want to predict what the next word is. And this, what that next word is, the model will be predicting based on enormous amounts of data that the model has seen. It will predict certain probabilities, and it will learn that the next word should be mouse. And if you keep doing this iteratively, you develop sentences and paragraphs by continuously predicting the next word that comes in. These can also be adapted and trained to follow certain instructions, which you see in ChatGPT, which we'll be talking about later as well. Now, what is a large language model? I think once you take a language model and just scale it up, think like you make everything large. A larger model, the amount of data is large, tasks it can do is large, and the languages it can understand. Basically, it's a much bigger scaled up model, which is trained on scaled up infrastructure and scaled up data. Going into, sorry, of course. So going into a brief history of large language models, so I think this is a quick timeline. I'll be touching on certain touch points in this and discussing them while we go through this. So starting with 2000s is where we kind of got into more a neural network kind of world, where the idea was you take a certain context and you try to predict the next word given a certain context. So it could be there are 5 words and you are trying to either predict a word in the middle of them or around them, and it could even be like different features, say a number, like a vector of numbers, and you're trying to predict housing prices or whatever. So we were talking, delving into the world of neural networks. So what is a neural network? It's something which was inspired by the human brain. It usually has 3 components. There's a forward pass, there's a loss calculation, and based on the loss, there's a backward pass. The idea behind it is that once you take a certain feature vector, x1, x2, you pass it through a certain set of neurons. These neurons are weight matrices, so it's purely matrix multiplication happening. Word after, like layer after layer, you end up with a certain prediction value, say a ZF. Uh, you have a ground truth value. So let's say the example would be you're trying to predict a house price. You say that the house is maybe worth 5 lakhs or 500K dollars, but the true value says that the house should be 900K dollars. So you calculate this loss. There are multiple loss functions here. So you calculate the loss and then you back propagate this loss through the weights. So the update would somewhat look like the new weight matrices would be the old weight plus some change, which is calculated based on a gradient. And the high level goal is that you want to update the weights such that the next time or like in future, when you pass the same vector input, the final output would be close to 900K. So you eventually start fitting on the data distribution. Uh, so I think everybody might have heard of these words. What is an like encoder decoder? But at a very high level, encoder decoder is a design principle. the idea is like, think of like a function composition. So you have a certain input, you encode it into a certain value using a function, say gx, and then you take the gx, which is basically correspond to the embeddings in the terminologies, and then you decode them back, decode them to a certain another value, which is another composition like f of g of x, and you eventually end up with the desired outputs. So the meaning is that encoder understands the input, embeds it into certain latent space, which is like embeddings, and the decoder takes this encoded information and decodes into the output space. So this happened, and then somebody came up into 20, and this went on for a long time. And in 2017, we were introduced to the idea of transformers. They came up with this idea of attention mechanisms, and the idea which kind of revolutionized the entire industry. So what are transformers? The main component of the transformers is really just attention. The research paper was called Attention is All You Need. It's essentially an encoder-decoder structure, which is composed of transformer blocks. So each of this thing that you see on the right is a transformer block. And both the encoder and decoder are essentially these blocks stacked over one another. What this transformers allows us to do is it allows us to model sequences. So for example, if there's a translation task, you want to convert the sentence into French. So you would take this, I am a student, it would encode all of this information into an embedding, which is somewhere here. And this goes into the decoder and it outputs something like Je suis étudiant. I'm probably doing some bad pronunciation here, but that is what we end up with. So, and the important part is while decoding, we are only looking at the words which have already been predicted. So when you're trying to predict étudiant, you are only looking at Yesui. So that is the idea. You use the encoded information along with the already predicted information and predict the next word. So self-attention, I think we have all heard of it. We have all come across it, but let's dive a little bit deeper into what it really means. So it contains of three components, query, key, and value. The idea is like there's this entire pipeline which I'll be going through over, but the formula essentially looks like query into a key transpose, some scaling, some probability softmax, and multiplying by v. But what does it really mean? So query, key, value are in self-attention, they are basically the same thing. So by self, you mean you are attending on yourself. As a first step, you take the query key and value. You can get those values by taking the input embedding values. So let's say this sentence, hi, how are you? We have a 5-dimensional embedding for each of these words. You multiply it with the linear weight matrix and you end up with the query matrix. So this is the query matrix. Similarly, you have a key matrix, and similarly, you have the value matrices. Since the weight matrices on which we are multiplying are different, the final Q, K, and V are also different, but they still represent the same word embeddings in a different space. So once we have these values, now we get to what attention values really are. So this is where we look at this matrix multiplication. So we take the query matrix and we take the key matrix and we do a transpose of the key matrix. And now we end up with this 6x6 probability score, if you want to call it, or maybe correlation score, if you want to call it. But these are really the attention values, which basically tells that like this 89 value basically means that high needs to attend to high more than it needs to attend to this comma. So basically, when you'll be generating the final value, this determines how much importance you should pay to the other words in this sentence or sequence. Note that because we do this multiplication without getting into much detail, we do increase the variance of the data, due to which we have a scaling factor, which is the square root of the dimension. The dimension here is 3. So you divide all of these values eventually by the square root of 3. So yeah, we end up with these attention values, but they are very big, right? Like when you want to eventually convert them into certain probabilities, and that is where the idea of softmax comes into play. So the idea is like once you get this attention filter, the values on how much you want to attend to a certain word in the sequence, you do a softmax and it end up getting a probability distribution, so that once you look at this first row, the word high will attend to all the words in this sentence by this much probability. So so these are also called the final attention values that we have. Now the question is, what do we do with these attention values? Right? So what is the entire point of these attention values? So the idea is like you eventually multiply them with the value matrix. So if you remember, the value matrix was derived from the input word vector itself. So when you multiply and you do this matrix multiplication, you will be doing say 0.42 into this value, 0 into whatever value, and you'll be finally essentially doing a multiplication on the word embeddings that you had here, but based on this probability. So a more intuitive thing to think of it like is this. So if you have an attention filter, which is say a white like this image, and you only want to you only want to get the empty space in it and not get the gray space, you are multiplying ones on this original image and zeros on the grayed part. So you end up with this kind of an image. So it is somewhat of a filter on the actual values where you are also aggregating the information from all the other words in the sentence or in general a sequence. So yeah, this is basically the entire pipeline, and we end up with a certain word embedding. So you'll end up with, for each of these words, you'll end up with a three-dimensional word embedding, which will be eventually used down in the further processes. So yeah, this happens. We come up with attention mechanisms, which transforms everything. Things become faster because all of this calculation can happen in parallel. They are much more effective. They are trained on much larger amounts of data, and we start getting much better models compared to the older LSTM models that used to exist. Uh, so now comes like the application of this. So now we have the transformer architecture, and now people start creating different architectures by combining these blocks in different ways and creating various designs. So BERT came, which is a bidirectional encoder. Essentially, the idea is it's an only encoder model. So if you remember, transformer architecture had two components, encoder, decoder, but in BERT they only decide to go with an encoder. So the idea is you end up with an embedding for each sentence or for each word, and you can use various design principles to get to that. Then also came GPT-2, which was a decoder-only language model. And this kind of started the revolution of generative AI where we are today. So what is GPT-2? GPT-2 is basically GPT stands for Generative Pre-trained Transformer. The reason it is generative in the sense is that there is no information being encoded. We don't have a sentence. We just start with at a place and we just keep generating after that. The idea is we do this through masked self-attention, which is that let's say we have these four words already predicted, uh, robot, must, obey, and you're trying to predict the next word. There is no information being encoded. It's just a transformer block, but we are doing live decoding directly. What this allows is that it allows you to generate whatever you want. So you can give any prompt. It will take, say, a prompt can be something like Sagar must play a sport. What is that sport? So it will look at all of these words and it will try to predict that sport could be football or cricket or whatever they know about, say me, you're looking at the data. So this decoder-only modeling, the model was trained on large amounts of data. It was pretty much a classification loss. So you try to predict the word using a probability score, and then you back propagate it through all the layers like we discussed in the neural networks setup. And the number of parameters of these models were 1.5 billion, which are a lot. So even if you just wanted to store these parameters, it would take 3 GB of RAM just to store this model, and then training obviously takes time. But this is where the entire revolution of generative AI started. And then we came up, like in an year or so, OpenAI came up with GPT-3, which was 175 billion parameters. So it was 150x scale on GPT-2. GPT-2 was a good model, but it wasn't a great model. So the generations were a bit scrappy. You wouldn't get what you really wanted. And the idea was, can we scale it up and get something out of the models which we haven't seen up until now? So this model was trained on much larger amounts of data. It was trained on 300 billion tokens of data. So you can think of, say, each token is, say, about, uh, say, like approximately like 2 bytes or something, maybe even more, depends on like what kind of tokenizer you use. Uh, but you end up with a lots and lots of data, and you need to store it and then train it. So it takes a lot of time and money. But what happened with this scale is we discovered something which is called emergent properties of LLMs. So what are these emergent properties? Essentially, are that the LLMs which were supposed to do certain specific tasks in supervised learning, in which you would train a model to do a certain specific task, we suddenly saw that the models which were not trained to have certain abilities could do them. So the model was not really trained to do math. It was not trained to do specific question answering. But suddenly we saw that, with the right prompting or right context, it could understand math. It could understand uh, context. It could frame completely correct sentences and various other things, which was not possible with a smaller scale. In research, it has been shown that these properties are generally seen after 30 to 40 billion parameter range. But with as we progress in technology, we are also able to get them for smaller parameter ranges as well. So what this GPT-3 model could do, it had two big things. So it had great one-shot capabilities. Like if you give it the context, I remember like 2 years ago, we used to like play like 2, 3 years ago, like there was this API, you would teach it like 5 + 3 is equal to 8. And you would even teach it like give examples of multiplication. And when you asked it to do that, it would be able to do it. So it had great one-shot capabilities. So you could do much more complex tasks like reasoning, inference, and so many other things. But it also had decent good shot, zero shot capabilities. It would do very simple tasks, but not really, they were not really game changing in many ways that you could just use it for uh, daily use and like ask it various questions without giving it the context. But it became a foundational model on which a lot of further research was done, and uh, like a lot of what we look at LLMs today were derived from. So this is the first large language model. Before this, we had language models, we had encoder decoder models, but this is when things became large because we had like 175 billion parameters. Um, so what came next is two different game-changing things in about 2 years of research, which were Instruct GPT and Chat GPT. ChatGPT was a more user-friendly manifestation of Instruct GPT, but Instruct GPT was a model. It's also a paper by OpenAI, which introduces reinforcement learning for human feedback and shows that how we can teach models to follow certain instructions and really talk like humans, which was the game-changing part of most of the uh, game-changing part for ChatGPT as we see it today. So, what is reinforcement learning? So the idea is like it is derived from how humans or animals learn, which is probably true for most of the machine learning space and neural network space, is that you have a policy or like, so think of like, I'll start with this rat example, right? So rat is in a cage, you show it a positive odor, they go and they get a certain reward. The rat goes if there's a negative odor, there is punishment to get there. So similarly, you have an environment, uh, you perform an action in that, you observe the environment, you perform an action on that environment, and based on that, you get a reward. Once you get the reward, you learn something that, okay, so if I do a certain action in a certain environment, I am either punished or rewarded. And then once you learn this, you can eventually improve your mental algorithm. This is how we do most of the learning in real life. You touch a hot pan when you're a kid, you realize, okay, this burns, I'll not touch it again if it's hot. Something like that. So in a more technical way, you have an agent, which is there's a policy, there's a learning algorithm. You do an action in a specific environment, you get a reward. You observe the reward, and based on the observation, you modify the learning algorithm and the policy. Um, in a more equation-like term, somebody's interested in it, I would say, so think of Q as a function which we learn for a state and an action. State represents the environment. So you have an expected value, or like you can call it a reward of doing action A in state S and then following the optimal policy afterwards. So at every time you are trying to learn that in state ST, if I perform the action AT, uh, what will be my final reward? And then you try to learn this function based on this equation. And essentially, you are reinforcing the behavior based on the rewards obtained. So how does this work for like language models and like the RLHF? So RLHF is reinforcement learning, but from human feedback. So the reward is being defined by the human because that is pretty much the best kind of reward we can actually give to the language models because we are trying to emulate language. Uh, this is a snapshot from the Instruct GPT paper, but the idea is so if you think of it, what reinforcement learning needs, right? It needs a way, it needs an environment, it needs a way to get rewards in that environment, and it needs a way to keep performing those actions and learning. So usually the step one is when we are training a model is that there's a prompt, explain the moon landing to a 6-year-old. Some people wrote what the actual output should be, and you trained a fine-tuned model on this. So it is like supervised training, you train a model. So you get a better language model. This is not reinforcement learning, but this is a step we're getting there. But now we have, so now we want to define what a reward is, right? So we take a prompt, we get several model outputs. So explain the model, explain the moon landing to a 6-year-old, you explain gravity, explains like your moon is, there are multiple responses. There's a human labeler who ranks these responses, like D is better than C, whatever, right? And then we use these ranked labels to train a specific reward model. So this is a separate model which we train based on these responses. And the job of this model is to give a reward based on a certain output. So in the future, when we like send a response to the model, the reward model would give us a score in return. And then comes the final part where we learn the policy or like the learning algorithm that we talked about. So once, so how the flow works is that you would give a prompt, you send it through a model, which is policy, essentially defined on top of this fine-tuned large language model that we had. You define a policy on that. So this, based on the policy, the model will output a certain sentence, say once upon a time, whatever, whatever. We send this output to the reward model, which is already trained on human outputs. Reward model would return back a score. Let's call it RK. And then we use this score to back propagate through this policy that we had defined earlier. So you're taking reinforcement learning and modifying it for human setup, where the reward is defined by humans and we train is defined by humans using a reward model. Some caveats here or like interesting things to know is that this was uses a proximal policy optimization algorithm. I won't go into the detail of that. but if you're interested, you should read through it. It was developed after a lot of work on reinforcement learning. There were multiple other policy optimization algorithms, but if you're interested, you should go through that. Uh, and yeah, after that, once we do all of it, we eventually end up with a pipeline, or like this, like once we train the model through this pipeline, we end up with a policy. And this policy, PPO, or whatever this is, we once we have this, we can deploy it. So whenever we somebody comes up with a prompt, this output of this will be more accurate because we have back propagated it based on the reward model. Okay, so all of once we had all of this, now and we ended up with ChatGPT. So this is how we end up with ChatGPT. You kind of improve the reward model, improve the policy, keep training it, and you end up with a much more refined ChatGPT model. But so what then came GPT-4, right? So in like about 2, 3 months, we have already discovered the emergent properties. We know how big models help. We also know what how to reinforcement, like how to train it. And by this time, we have OpenAI has collected a lot more data based on user preferences and always using human laborers as well. So now we end up with GPT-4, which is a much bigger model. The information is not really public, but it is like conspiracy theorists say that it has about 1 trillion parameters, which is a lot of parameters. Like it would take like terabytes of like what space to do this. But yeah, I mean, we know what GPT-4 does. And I mean, there has been a lot of progress after that. We have seen a lot of different models come for specific use cases after fine tuning, Palm models, there's MedPalm, and basically a lot of domain specific LLMs as well. A lot of open source LLMs as well. So open source LLMs have allowed us to like do much more research, improve these models, and also deploy it for various other small use cases which we cannot use GPT directly, either because it's too expensive or not directly doing a great job on a very specific use case. And this is something which will keep continuing. We'll have keep having better research and better models. So coming to the real world application. So now we have a LLM. GPT-4 is widely accepted that it is the best LLM, specifically if you want to do multiple tasks at this point. Uh, and it's also the biggest model that exists in the market right now. So what are some real world applications of LLMs? I'll take some examples. So for example, DeepScribe, right? So it does smart electronic health record compatible medical note creation, which helps doctors save time. Then we have GitHub Copilot. It allows you to auto code complete. Everyone can be a developer basically. You can like give it prompts even and ask it to write certain codes for you. And we have law firms that will pass through large amounts of data. You can write large documents. You can reason with the LLM as well. You can ask it to extract specific Q&A with that data. There's been a rise in call centers, which are more like chatbot agents kind of a thing. Essentially, if you give a call, they'll ask you to, instead of a human, you will hit a technological chatbot where you'll talk to the chatbot for a long time until you get to the real agent. It can be sometimes annoying as well, but that is but it saves a lot of time and money for these companies which are deploying these. Basic writing, stories, articles, even education. You can create education content, do Q&A on a lot of content. And probably the final most diverse thing is you can create multitask agents. You can train agents based on specific prompts to do certain specific tasks for you, which is another big, I think, a very generic term to put it in, but it is also how many people have deployed the large language models. So an interesting thing to note, if you would look at a larger picture of the real world applications, is that this language model is very good at writing in general, writing anything, writing code, writing documents, writing uh, like research papers or whatever. And because it's good at writing, and the context on which it writes is also important. So it's also very good at understanding text, understanding language, and then writing based on that language. So that is the real power of LLM, like understanding language and being able to read and write. There have been a bunch of startups which have come up. There are two, so for any large language model, there are two domains. One is the infrastructure layer, like the infrastructure on which you'll be training the models, on which you'll be hosting the models. So things like NVIDIA GPUs or OpenAI infrastructure for calling GPT-4. There are various other AW, you can use AWS, Google, Microsoft, Hugging Face, so many things which allows you to which gives you the code which you can use to create your own model, train your own model, and even host it. But then there's an entire application layer where you can use all these infrastructure to like develop products, right? So you can have these. There's so many these writing companies like Hyperwrite, Cohere, Copy AI, and like various other companies which allows you to write based on the context or based on like whatever context you want, but you use these models as a base to write the content. Similarly, GitHub Copilot. So that is the idea. There are two versions of it. One is like how to create the language models, how to use the language models, and then there is this application, like developing all of this into a product. And both of these are very useful and very important parts of the space. So I'll go a little bit into a bit more detail of the technical part. So the major technical challenges in training an LLM, training your own LLM or even fine-tuning an existing LLM is the model size is the large part in the like LLM. The large models are too big for a single machine to handle, so it won't fit in your GPU. Even like say the latest open source biggest model, the Llama 270 billion model, it doesn't fit in a GPU. You need like multiple GPUs to fit that model to train. So you need a setup to distributed training. There have been a lot of research and techniques which have come in the research domain, which have allowed people or machine learning engineers to do that. One of the most popular is Zero. It's a zero redundancy optimizer, which allows you to have very efficient parallelization and memory partitioning. This includes data, model, and pipeline parallelism. I won't go much into the details right now. A counterpart to this is FSDP, which is fully sharded data parallelism, which is from PyTorch, whereas Zero is from DeepSpeed, which is a part of Microsoft. The other technique which is often used to control model size is quantization. So if you know any float value is a 32-bit value, which is 4 bytes, but you can also store this in the lower bit precision. You can store the same numerical value in say 4, 8, or 16 bits. And when you do that, you save on memory because memory is basically how many bits you use in storing and operating on it. So there have been a lot of models which have been trained on say low bit precision, and this has allowed people to fit a 70 billion model say in a single GPU or even on say a if you have a Mac or like a Windows laptop, like on the device GPU by using this quantization. Although we do lose on accuracy with this because the precision is lower in calculation, but with enough work, you can get close to it. So you won't get a perfect model, but you still get a decently okay model. Long training times, and for that we have solutions like low rank adaptation, which helps replicate similar performance by training on much fewer parameters. This is also research supported. Then there are challenges on understanding very, very long sentences and paragraphs. So you need to attend, like the attention that we talked about, you need to attend to large number of words in the context. And this time complexity is usually quadratic when it comes to this. So there are new techniques like shift short attention, which are an approximation, but they do a good job when it comes to such large context. And then we also have things like we have a model which is trained on a certain context length, which means that it was trained to predict or understand sequences up to a certain length, like say 4096 tokens. But what if you want to predict 8,000 tokens or 10,000 tokens? So there are techniques like position interpolation, which allows you to do it with the same model. So you don't have to train a new model for that. Yeah, so even with all the powers of LLMs, I think it's important to be critical of them to understand where they lack. So a few examples here. One big problem is hallucination. So this example you'll see, you're trying to predict like who is Noble Atkinson, and they'll end up with like some random information, the social activists, tech ventures, initiatives, like so many things which are not correct. Then there is also harmful information. So how to kill someone and not get arrested? It's not a thing that you want to give an answer to someone. It's harmful for the society and it has ethical concerns around it. For this has been fixed by and large by OpenAI on ChatGPT. You hardly get these responses anymore, but there are always hacks around it, and there are always some news articles where you'll see someone got around the protective layer of OpenAI. And then there are ethical concerns around, for in this case, around art. There was this huge strike where Hollywood writers were striking. Uh, so that was like because everybody started using ChatGPT for creating stories. So now, where do you get the human creativity anymore? But the reason for strike is even more ethical, which is that the data on which the ChatGPT was trained or these models were trained was written by these writers, some other writer somewhere, and model is learning from that. So there were ethical concerns around this. And then obviously, like if you start doing like you can write a story using this is a prompt that I gave. So write a story about whatever prince and it will come up with a story. So then why do you need writers, right? So there are a bunch of these concerns which need to be addressed for a holistic societal use case where, and I think we'll get there slowly, like with more improvements, more data, more training, and understanding these models more and more, and also tuning these models so that they can be more useful to the society and people living in it in the long term is where and how we get the best out of these LLMs. Yeah, so I have a 5 minute Q&A slot if about these, and then we'll go on to the second part of the presentation.
Thank you so much for that. A lot of information, a lot of really good information. We do have some people that are asking for either the deck or a recording, and we do just want to let you all know that this will stay on our LinkedIn page, and you can also visit High Counselor on YouTube to be able to view this. So I'm sure that we'll have some comments and questions coming in. Go ahead and feel free to drop any questions or comments in the chat. Let's see. It does look like we've got a comment here, so I'm just going to read this. So I'm happy to kind of moderate. So we've got one viewer that is saying coding programs is based on algorithms, which is based on logic. Could we code programs using human language now? So using ChatGPT to program an application. I know there will be a lot more involved, but could ChatGPT save a lot of time and money?
Yes, can you also paste this question in the chat if possible? So that
Sure.
I answer all the components of this.
Yeah.
Uh, so the question is, could you code programs using human language now? This is true, we can actually. So the idea is like even I use it every day, so many of my friends use it. So if you prompt ChatGPT the right way, that so I want to write a loop which say gives you prime numbers up until 10, it will write you a code snippet which will actually work right in the first go when you run that. So yes, we can code programs, you can even code applications, but you'll still probably need to ask it to write certain components of these applications, and then you probably need to join them together. uh, but yeah, I think as we go forward, this is the future that will be coming, say, in the next 3 to 4 years as we get more advanced in this. These code that the ChatGPT writes will get better, it will get more accurate, and it will also allow you to uh, pass in the context. Say, if you have written a certain layer in an application, you can pass that layer in the code, and then it will write you the remaining code so that now you can run this application. So yes, you're absolutely right.
Perfect. Let's see. Ritesh has our next question.
Right. So fine tuning open source LLM. So I would say it mostly there are. Let me go back a bit of the slides. Let's talk about. mm, I think this is more technical. We can use this diagram. So the idea of any fine-tuning in any workflow is pretty much around you need three components. One, you need the right data, you need the right model, and you need the right infrastructure. I think these are the three main components. The data part is something that you have to figure out, like what is the specific task you want to train it on. Do you want it to be better on, say, translation? Do you want it to be better on your domain specific use case? You collect the right data. What that data would look like is something you have, say, an input sentence, input query, and then you have an output. So this is what the output should look like. And then you use that data to train the model. What then comes the model choice. For the model, you use open source LLM. So let's stick with one example, say Llama 2. Let's start with the 13 billion model, right? It's easier to fit in a GPU. You take that model, you use a certain specific open source library. There is a lot of code available on Hugging Face. Then there are open source projects on GitHub that you can use. So where you can pull this model, pass in the data, and train the model. So yes, you need to pick the right model. Uh, the right model choices also depend on context size that you want to train on. And the third component is the infrastructure. I think I'm afraid that is something that you need to pay for usually, unless you can fit it on your own machine, on your own laptop, or if you own a GPU, that's amazing. But otherwise, you usually get some credits, or you can like host a VM on, say, any of these cloud platforms, uh, Microsoft, like Azure, AWS, Google Cloud, and so many others these days. And you usually need to create a machine on that, put everything on that, and then train on a GPU based on the model that you picked, the code that you picked, and the data that you had.
Thank you so much for getting these questions answered. So we've got a LinkedIn user that's asking about some unique challenges regarding debugging.
Oh yeah, I think that's so I think most of the challenges that come with LLMs are usually centered around this part, like the model size and long training times. So I think often when there are bugs in the model, they would show up much later. So let's say you already spent half a day or a day training that model, and then now it suddenly errors out, right? So, and now you have this entire output log, and because it's also trained on large amounts of data, you really don't know what went wrong in that part. So I think it's very subjective what you are trying to find, what your intuition is. But I think uh, yeah, I think like the challenges really is around the distributed nature of it because of the size. So because a model does not exist on one machine, even a machine failure can cause a problem. Data incorrectness can cause a problem. System crashing can be a problem. There can be so many other things which can create these problems. So I think the unique challenge is really the size part. The way to fix it or like get around it, I would say, is uh, around like either first make sure that like test everything on a smaller model. I would say use the same data but train it on only a 1 billion parameter model. It will be faster, and you can look at the outputs actually. Like you can ask it to do one output at a time, and then you can look at what the output was. So that is something that you would want to start with. uh, and let me think. I can think of other big challenges which I'm like not striking right now. They can be like data errors, right? So often the tokenizer, like once you have like a one like 10 gigabytes of data in a big file, uh, it can often be the case that there are some faulty data in those files. So you need to have various data validation scripts or deduplications of these to make sure that there is no duplicated data in those scripts. So I would say again, think of it like data, model, infrastructure. These three are the big components. So you would ideally, and the size is the biggest problem in all of these three different components. So you need to make sure that you do everything on a smaller scale, test it out robustly, and then do everything else.
Great, thank you. We are, and we've got two more questions to answer, and I do want to get to those, but I want to make sure that we get to the rest of your presentation. So let's jump back in Unless you
Yes.
want to go ahead and answer these, but I think we can get to these maybe at the end. Is that
Yeah,
okay?
let's get to them at the end.
Perfect.
We'll
Perfect.
have a 5 minute Q&A then. Cool. So getting to the part two of the presentation, like this is more about the career, and I've tried to center it down around like young professionals and students. So how do you get into NLP? NLP is the foundation of large language models. So as a student, this is also a lot of personal experience that I'm sharing. So a very easy way to is to get into like school and college courses. There are machine learning, AI, NLP, lots of courses these days which are offered in the colleges itself. So you should get into that. A thing to do in like high school would be to get into coding, just general coding. I don't think you really need to get into LLMs as much unless you are super interested, in which might you might as well. Uh, I would still say focus on the fundamentals, try to understand how these machine learning models work before you just start uh, like creating random models and then you have to debug and you don't know why they are going wrong. So get a rough understanding of things and then just play around with it. Another important source is using online sources like YouTube videos. A lot of people have very good tutorials. Coursera courses by great professors in the industry. Medium blogs and Hugging Face also has tutorials. Somebody who is more already into it, I would say work with research projects, specific NLP, large language model research projects with professors in your universities. Try it out, try developing something which is useful, and you learn a lot just by doing the work, and also adds to your resume. Somebody who's even more excited, you go to start developing open source projects on GitHub. There are so many open problems, people are writing code, developing repositories, and you really get a lot of understanding through just by looking at code, reading it, and trying to add something to it. Now we go to somebody who is even more excited, which is like hackathons. So you can join hackathons, like try to again use, say, an LLM, either train an LLM for specific use case and showcase it. So you end up learning a lot. And obviously, higher education is the final way. Like if you uh, really want to get it and you don't have a lot of experience and you want to get it through a more traditional method, you go to a higher education setup. So talking about the industry or even academia, what are the different roles that you'll encounter in this domain? So one role which is a very more researchy is like the researcher or researcher role. It is essentially you can either be an academic researcher or industrial researcher. The job mostly centers around reading papers, building in-depth understanding of deep learning systems. You try new ideas, experiment, and then you come up with something new. It works, and you publish paper in conferences. The what you achieve is that you drive the field forward by creating new research, which people like people who are more in the applied setup use, and they develop products on that. So you more are on the fundamental foundational layer of it. Academic researcher would be somewhere in the university as a doctoral student or a postdoc student or even a researcher or professor, or in industrial you could join just as a researcher in so many of these research labs that these companies have. Another role which is often talked about is data scientist. In my opinion, this is a very overloaded term. It can mean anything from a data analyst to a researcher to a machine learning engineer, depends on the company that you're really working with. It's usually an industrial term. I would say if you're being offered that role, you should always understand what that role truly will be. Like, what is the work that you will be doing, because it can be pretty much anything. Then an applied scientist or an NLP ML engineer role. This is pretty much an hybrid role, which requires you to have research as well as engineering skills. The goal, it's an applied role, and the idea is that you find the best technology that exists for a product. So you find the best LLM for your use case, you modify it to your use case for your product, and then you put it to use. You deploy it, and you actually have customers using that product. So, motivating thing here is that you actually make a difference to the world by like creating a product that people are using. So you will end up doing that. And the final role, which is also pretty popular, is an ML infra engineer. This is not really an NLP role, but more of a machine learning role. And it is much more engineering heavy, where you develop the foundational stack on which the infrastructure on which the model is trained. So how the GPU parallelization will work, what data should flow where, how to make it fast and efficient. And you're expected to make like these platforms which these models will run. How to land an interview? I think this is very generic advice, honestly. So you improve basic skills for NLP projects, you highlight them. Reach out to specific managers and express your desire and motivation. Specifically, if you are not already in the field, try to find roles and managers who might be open to uh, like you need to express your desire and kind of show how motivated you are to get certain interviews. I would also say do your homework. So you need to read about their work, like what the team does, and see how you can actually add value. You can add value in various terms. You can even add value with your engineering experience or some other research project that you did, which is not even NLP. But you need to kind of see how you can add most value to the specific team or the company or the product that they're building. And specifically for someone who's not already in NLP and looking to get into that, I would say you need to understand that no job is just about NLP. You need NLP, sure. You need to have a basic understanding of things, but you need to have a bunch of other experience that comes with it. Uh, Even when I moved to NLP, I had a bunch of other machine learning experience, and that helped me a lot in getting NLP roles because no job is really just about NLP. What are the skills that you can expect to be tested on? I mean, this is coding, lead code kind, which is like standard algorithmic problems. We have coding ML, which is usually around, like, say, code a k-means or code the backpropagation algorithm or some other algorithms. They're only usually asked in research roles and applied roles. The ML depth role is something where you kind of dive deep into a specific project or a technology and you talk about that with the interviewer. They'll ask you specific questions, how you handled certain challenges, trade-offs, and what was your thinking behind it. And the idea is to understand how well you are versed in the entire setup. Then there's ML breadth. This is the idea to understand, like, do you have a very clear understanding of the basics in ML work, neural networks, classification, and very standard things which any ML engineer or researcher should generally know. Uh, then there's system design. It is usually people who engineer roles which find a bit challenging, and it is often also not asked if it's a very junior role. But in research role, it usually takes the form of machine learning design. So you take a machine learning problem and solve it end to end, trying to figure out how different components will work and interact with each other. And for an infra kind of roles, they kind of become more like how will you develop and scale a system end to end so that you can train big models or deploy something which is going to be used by, say, 10 million users or something. How to get these skills? Yeah, I mean, various other things like you go lead code, geeks for the geeks, understand data structures, try out things, keep coding, read books, blogs, and things that I talked about. There are a lot of online courses for system designs uh, and ML design that you should take. And obviously, you need to practice interviews. I think this practice interviews are really helpful. Ask a friend to do an interview with you or some other senior or anybody who has an understanding of this field. So where is generative AI headed? So I think we talked a lot about what LLMs are right now, how they're scaling up, how it's so easy to use GPT-4. But the question is what comes next? I think in my opinion, there are a few things that are very important to solve. One is accessibility. Right now, the models are very big, so no one person can really host the model apart from a big corporation because it's expensive. Uh, but we want to make it smaller, cheaper, and effective. So there was a recently only a 7 billion parameter model which was released. Mistral 7 billion. It does pretty well on certain tasks. It is not as powerful as GPT-3, but it is able to do certain well on certain specific tasks. Uh, and we also then start working on fixing challenges like hallucination and harmful information and ethical concerns and all of that. So there will be a lot of work going into that. Also, the understanding of like how these models work, more explainability added to the models will also be important. Then the idea is expansion in the domain of computer vision. Right now, we are talking about LLMs, language models, text. But I think a big part of generative AI is also image, video generation. We already have decent image generation. It's not great, but it's okay. Video is still pretty far away. We are getting there. Some companies are doing a good job, but we are still a bit far away. We have a DALI series of models of multiple technologies. And if somebody already has these latest Android phones, you'll see things like image inpainting, and say iPhone has image segmentation as well. So you basically click on a picture, it will segment images for you. So these are all sort of generative AI and model vision capabilities, but these will keep getting better and it will be more usable for everyday user. Then we have multimodal AI. So you multimodal essentially is like we have text, we have image, and now we combine everything together. So you process text, sound, and images all at the same time. Something like what a self-driving car would do, right? So it would read a sign, it would take an input around what around is happening in the form of sound, and obviously you take image and video input happening. An interesting thing to see is that ChatGPT already has some of these capabilities with like the new paid version. So if somebody's curious, you should try it out. You can actually give it an image and it can do an image analysis for you as well as text analysis for you all at the same time. And the final goal, which most of the people in the industry talk about, is artificial general intelligence. And the idea is that we build a computer which is pretty much like a human brain. It can do everything that a human can do. It is still a bit far away, but it's very hard for me to hypothesize how long we're going to get there. But we need to address a lot of these initial concerns to kind of get there. It's going to be some time, but we'll get there, is something that most people believe. So, yep, there are certain resources. I think we'll share that separately. Some links around design courses, blogs around how all of these algorithms we talked about work. And yeah, that's it. Thank you everyone for being with me. We can do a 5-minute Q&A.
Perfect. Thank you so much. That even just sitting here and listening to this, I learned a lot, and so I have no doubt that that our viewers that are in the field really got some valuable information from you. So thank you for being with us. Viewers, I'm going to turn it over to you. So continue to drop in the chat any questions that you've got. We do have 2 questions from before, so I'm just going to pop those on the screen and give you a second to review and answer.
What is the best LLMs for text embedding? Or there is no intended flow building and fine-tuning models. So I would say like LLMs are, I mean, any LLM model would be fine for text embeddings. The idea is that the output of an LLM is usually a word or a predicted value. So you'll have to go inside the model and extract a hidden layer weight matrix. So a standard, I would say the biggest LLM is the better for text embedding. So if you want pure word embeddings or sentence embeddings, I would say go with the biggest open source model that you have, which is the Llama 270 billion. Just to get the text embedding. So now you would like to use your own data, and what would be the flow building and fine tuning? What would be flow building and fine tuning models? Okay, so the flow is again going to be pretty similar to what I talked about. So you already have your own data. I would say you need to create 3 components. One is what you want the model to do, so like a prompt. Like you are a medical assistant or you are a AI assistant in a law firm or whatever your firm is. You talk about that. You give and your job is to do something. You give it the exact instruction, like convert your data into the exact instruction that you want the model to do, and then you have a response that this is what I want the model to predict. So you create this data. The second part is you get a GPU somehow, either through cloud or your own machine, or you figure out how to get a GPU. You can also do it on a CPU, but it's going to be much longer and much slower. And it's going to be just much more slower. So maybe you find a way to get a GPU. You whatever that platform is, you get your data there. And the third component is like a script, a code which will take the data, convert it into the right tokens, use the model and train the model. And for that, I would say go for some Hugging Face tutorials, play around with the code, fix the code, or there are a lot of open source repositories. I can name a few if you want. So there is one repo called Axolotl, which is an OpenAI collective. It's a good repository which has a lot of functionalities. There's also a TRL repository, Transformer Reinforcement Learning by Hugging Face, which is also a very good repository to use and start training a few models.
Perfect. Let's
Oh,
see.
one thing that I can add actually is like inference, which I didn't talk about a lot, is like you would ideally want to define certain metrics like perplexity, which is basically confusion, or like how loss is doing on an evaluation set, to understand how well your model is training and whether it is converging or not. Sorry, yeah, next question.
Yeah, no, that's perfect. Thank you.
Can you provide me with something to make this plan more explain? Oh yeah, that's a very good question. I myself was working on explainability of these models about 2 years ago. They were not focused on large language models, but my work was in general neural models. Uh, if I'm being very honest, I don't have a very great understanding of how or what we can do to make these specific large models more explainable. But in general, I would say uh, any process to make a model explainable is to uh, like the research is around there's an input and there's an output of any model, any black box model, and then you try to understand what would happen if you were to change an input. So let's say you have a word, I am a student, and you're converting it into French, right? And and there's an entire weight values which are created in intermediate steps in the model when you run it in the forward pass. You would ideally, and then this is one example. The other example would be now you pass in, I am a teacher, and you would convert it into French. So you have these two examples, and both of these will have their own weight activations. And then you will compare these weight activations that uh, when the model was processing this input, what were the intermediate values? And then you try to look at that and what different attention values were high, what were lower, and you try to develop a holistic approach. I completely agree that it should be justified to make it more interpretable. If you're interested, you should read into things like SHAP values. There is a neural additive models paper on explainable models. It will give you an idea as to how people are doing, how they're explaining in general neural networks. So this problem is not about just LLMs being explainable, but the entire industry is working to make neural networks more explainable.
Great. And then we do have one question that I can answer. And so that is, are viewers going to be able to watch the recording afterwards? So again, this will stay on our LinkedIn page, and then you can also visit High Counselor's YouTube to view. But we do have a question and would love to know your opinion on this. Will AI evolve the human mind?
Oh wow. Okay, so that's a good. I mean, again, I'm not an expert on psychology, honestly, but what I can say, like, what I'm hopeful for and what I'm not hopeful for. So I think, in my opinion, uh, humans humans are amazing beings. We have evolved over time, learning from our surroundings, learning from what is happening with new technologies. If you remember when the steam engine came for the first time, right? Entire workforce was changed. Now everything could be done by machines, and a lot of humans. Like there was an entire transformational thing, but we learned from it and we evolved and we learned how to use it and use it for our benefit. So I think when AI will evolve in the sense that uh, AI will keep getting better, but it will also allow humans to keep getting better. We will be using AI to keep getting better and better, and we'll improve the AI. So it's a loop. We get better with AI, we improve the AI, and then AI makes us better. So it will keep becoming an uh, AI in general, I think, will be beneficial for humans in the longer run. Like we learn to play with it. It's like any other technology that came, like a light bulb that came so many years ago, something like that.
Perfect. Thank you. Thank you so much. And thank you all for for tuning in and for joining us today. I do have a couple links that I do want to drop, like I mentioned. So we have got some good information to share with you. The first thing that I want to share with you is the feedback form. And so feel free to give both of us any suggestions or feedback that you might have, whether that is over today's presentation or just the webinars that High Counselor hosts in general. Additionally, we have got an info session tonight. So feel free to register for that info session. I'm actually hosting it and would love to see you and to provide you even more information about High Counselor. I also want to share with you that we do have that cohort beginning on October 30th. So if you are interested in applying for that cohort, maybe you've already attended an info session, you've got all your questions answered, and you know you're ready to apply. And you know, again, some of the things that we are going to be able to provide you are things that were talked about in the presentation when it comes to the mock interview prep and the coding practice. So many great resources. So if you're interested in joining us, make sure that you click apply. And then we've got a job fair coming up. So if you are looking to hear from a few companies that are hiring, you'll get to hear from hiring managers or some people that are in those senior level positions. So feel free to sign up for that virtual job fair. That is going to be a lot of fun. And then we do have this real world live project. So feel free to register at the link below. And we would love to see you there and to help continue to support you as you grow in your skills as well. The last thing that I want to encourage you to do is to follow us on all of our social media platforms at High Counselor 2022 on Instagram, and then obviously on LinkedIn. It's just a great way to stay engaged with our content, to know what's coming up, what events we've got going on. So I do want to just say thank you again so much to our guest speaker. Sagar, thank you for joining us today. Any closing comments from you before we leave?
No, I think it was a great talk. I think it was super helpful to all the listeners, and I'm excited to just to feel that. I mean, I hope I inspired some people, some individuals to get into this field because it's gonna only get more exciting.
For sure, for sure. All right. Well, thank you all again so much. We hope to see you next time. Don't forget to fill out that feedback form so we can get that that valuable feedback from you. And just wish you a great rest of the week. So thank you all.
Thank you.